Hi everyone, Lesson 3, Endothermic and Exothermic Potential Energy Diagrams. The objectives for this lesson will be to identify whether a reaction is endothermic or exothermic just by looking at the PE diagram. You will label all parts of the potential energy diagram and determine how a catalyst will affect the pathway of the actual diagram you're looking at. So let's start with endothermic potential energy diagrams. These have positive delta H's. Remember, delta H is enthalpy, or the change in heat, which would be how much heat is either released or absorbed. So the product side to the right is always higher than the reactant side, which is to the left, meaning that energy is absorbed. So in a reaction, you would see the plus whatever kilojoules on the left-hand side because it's being absorbed. Okay, so now let's look at the curve. Notice products are higher than the reactants in the diagram. Okay, we talked about activated complex. This is the intermediate step here, okay, and that's where we want to get to. So we're going to label the following. We're going to label where the potential energy of the reactants and products are. We're going to label where the potential energy of the activated complex is, as well as the activation energies for the forward reaction and the reverse reaction, in addition to the heat of reaction, or the delta H, which is the heat of the products minus the heat of the reactants. So A will be located down here. Okay, and generally on these potential energy diagrams there will be numbers, and then that way you can read it from the side. So on the left hand side here on the y-axis you have potential energy in kilojoules, and then on the bottom is just the reaction pathway. Okay, so the reactants, the potential energy of the reactants would be at point A, the potential energy of the products would be up here at point B. Okay, the potential energy of the activated complex would be very top here, okay, that comes across this dotted line, and that's where we will put C. Now D will be located between the delta H, well actually you'd be subtracting this, so it would be the potential energy of the products and the reactants, okay? So the activation energy, or how much, the energy that is needed to get to this point, okay, from the reactants. So this would be letter D. This is the activation energy of the forward reaction. Now it's going to be reverse, obviously, for the reverse reaction going this way. So the letter E, the activation of the reverse reaction, because it's going to be going opposite direction now, is going to be here. It would be the difference between the products, the energy of the products and the energy of the activated complex. So that's where E would be located. Now F we're going to find between the heat of the products, which is up here, and the heat of the reactants. So that would be the difference here, okay, right between these two numbers. So you would take this value, which is B, and subtract it from A. So F is actually equal to B minus A. Okay, if that helps you. Now, the activated complex is the highest energy point of the reaction, the highest energy point. This is where full rearrangement of the reactants occurs. Most energy at this point. So remember, this must happen for the reaction to be successful. You have to get to that point. The rearrangement has to occur in order for that reaction to go forward. Okay, so now let's look at an exothermic curve. Now that we've looked at endothermic, exothermic is the opposite, basically. Okay, the exothermic potential energy diagrams, you're going to have a negative delta H. Heat is released. I don't know how that happened. Okay, so when you see a reaction, you'll see plus and then whatever kilojoules, okay, on the right-hand side. So the energy is going to be on the right now. The product side to the right is always going to be lower than the reactant side, which is to the left, meaning that energy is released. Okay, so now look, Our products are now lower than our reactants. It's the opposite. So the points are actually going to be the same for this, but the amounts would be different, okay? So potential energy of the reactants would be at point A, potential energy of the products down here, okay? The activated complex is right at that point, so we'll put C. That's the potential energy of the activated complex. Activation energy of the forward reaction would be this arrow here, so we're going to put D, and that's basically, we could say that D is equal to C minus A. Okay? And then the activation energy of the reverse reaction is going to be this arrow here, which is going to be E, and that is equal to B minus C. Okay? Now, heat of the reaction, same thing. Heat of the products minus the heat of the reactants. Since this is lower, then you're going to get a negative number. So it's actually equal to B minus A. Okay. Now, the activation energy is always going to be a positive number, so it doesn't matter. If you do B minus C, you'll get negative, but you're not taking away energy when it gets back up there. Okay, so this has got to be the absolute value of B minus C. All right, because it's just how much energy is needed to get to that point. You can't take away energy to get a reaction to go forward. All right, so that completes potential energy diagrams for endothermic and exothermic reactions. We will practice labeling these in class, but for an exit, I want you to answer these 3 questions and be prepared in class the next day with your answers. Okay, thank you.